Now we're gonna solve the Schrödinger equation for the harmonic oscillator using the analytical method. So let's start with the Schrödinger equation for the harmonic oscillator, which reads negative h bar squared over 2m, the second derivative of psi with respect to x, plus the potential term, which is 1/2 m omega square x squared times psi equals E times psi. To make things a lot more cleaner, we're gonna induce two new variables. The first one I think is called zeta, Greek letter zeta. We're gonna call it squiggly from now on. So squiggly is, we're gonna define it as the square root of mass times angular momentum divided by h bar, the square root of that, times x. And this is a dimensionless quantity, okay? And the second variable is k, and we're gonna define k as 2e divided by h bar omega. So in terms of squiggly, the Schrödinger equation number 1, this is it, will become the second derivative of psi with respect to squiggly equals squiggly square minus k times psi, and we're gonna call this equation number 2. So now our job is to solve this equation and find k, which is the same as finding E, the energy, and we're gonna have to find the wave function that satisfies this equation. So let's look at the first regime, which is when squiggly is very large. So when squiggly very large, it dominates over k. It becomes a lot bigger than k. And the Schrödinger equation reads the second derivative with respect to squiggly approximately equal squiggly square times psi. So now let's try to solve this dfq. We all know what's the solution for this dfq, and try it, okay? So the psi of squiggly equal some constant a times exponential to minus squiggly square divided by 2 plus some constant b times e to the positive squiggly square over 2. But at very large squiggly, as we assume, this is the solution at very large squiggly, right? This term, the b term, blows up, which is to say it's not normalizable. So the wave function psi is actually equal to some variable here, we don't know what it is, times the exponential term, e to the minus squiggly square over 2. Okay, so now our job is to find this set of functions that should go inside these parentheses. So if we assume just for the moment that these set of functions are h of squiggly, we can do that, right? And you're gonna see in a minute how we're gonna find exact solutions for these h's. So so this is psi. Let's take one derivative of it. So d psi d squiggly, just differentiate here, we get the derivative of h with respect to squiggly minus squiggly times h times the exponential term e to the minus squiggly square over 2. So let's take another derivative with respect to squiggly. Once you do that, you get the second derivative of h with respect to squiggly minus 2 times squiggly times DHD squiggly, okay, plus squiggly square minus 1 times h, and all of these times the exponential term, e to the minus squiggly square over 2. Okay, so now we have the first derivative, we have the second derivative, and let's try to put them back into the equation and see what we get. So now we have second derivative of h with respect to squiggly minus 2 times squiggly DHD squiggly plus k minus 1 times h equals 0. So now we're gonna solve this equation, okay, by a power series. So h of squiggly, it's a very popular method of solving these equations. It's equal to some constant a naught plus a1 times squiggly plus a2 times squiggly square plus a3 times squiggly to the third plus dot 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 dot. You see the idea? In general terms, this is equal to the sum when j starts from 0 all the way to infinity of a sub j times squiggly to the j power, right? So if we take one derivative of this, h DHD squiggly, we get 0. So a naught, this is 0. We get a1 plus 2a2 squiggly, right, plus 3 where are we at, a3 squiggly square plus 4 a4 squiggly to the third plus dot dot dot. In general term, this is equal to the summation when j starts from 0 all the way to infinity of j times a sub j times squiggly to the j minus 1. Correct? So let's take a second derivative. The reason we assume the solution as a power series. We take one derivative, we take a second derivative, and we take all of these and plug them back into this equation. Let's give it number. Let's call it equation number 3. So we assume the solution. We took first derivative, and now we're gonna take a second derivative, plug them back into equation number 3, and see if it works. So the second derivative of h with respect to squiggly is equal to, the first one is 0, so we get 2 times a sub 2 plus 2 times 3 a sub 3 squiggly plus 3 times 4 a sub 4 times squiggly square plus dot dot dot. So this gives us the summation when j starts from 0 all the way to infinity of j plus 1, this is the first number, times j plus 2 times a sub j plus 2 times squiggly to the j. Correct? So now we're gonna take these and plug them back into equation number 3. When we do this, we get the summation when j starts from 0 to infinity times the second derivative, which is j plus 1 times j plus 2 times a sub j plus 2 minus 2 times j a sub j plus k minus 1 times a sub j times squiggly to the j. This is equal to 0. Correct? So now we're gonna try to solve for this, okay? So now, due to the uniqueness of power series expansion, we get j plus 1 times j plus 2 times a sub j plus 2 minus 2 times j a sub j plus k minus 1 a sub j equal to 0. So we're gonna take this equation and solve for a sub j plus 1. So a sub j plus 1 plus 2 is equal to 2 times j plus 1 minus k divided by j plus 1 times j plus 2 times a sub j. So this is, we're gonna call it equation number 4 because we're gonna refer to it. Alright, so what does give us? Let's take the first term, a naught. So when a is the first initial constant a, we get, if j equal to 0, we get a sub 2 equals 1 minus k divided by 2 times a naught. But if we have a2, we can get a4, right? So a4 is equal to 5 minus k divided by 12 times a2, right? But we know a2 is in terms of a naught, so we can rewrite this as a4 equals 5 minus k times 1 minus k divided by 24 a naught. And then we can get a sub 6 in terms of a sub 4. So a sub 6 will be you know, some constant times a sub 4, and a sub 4 is in terms of a sub naught. So we can get all the even a's in terms of a naught. Meanwhile, we can get all the odd a's in terms of a sub 1. So a3 is equal to 3 minus k divided by 6 times a1. A sub 5 is equal to 7 minus k divided by 20 times a sub 3. But we know what's a sub 3, so we can rewrite a sub 5 in terms of a sub 1, which give us a 7 minus k times 3 minus k divided by 120 a sub 1. There you have it. So we have all the even a's in terms of a naught, and we have all the odd a's in terms of a1. So our solution, h of squiggly is made out of two h's, the even one plus h, the odd one of squiggly, right? And let's define these guys. So h even is equal to a naught plus a2 times squiggly square plus a4 squiggly to the fourth, and so forth. And then h odd is equal to a1 times squiggly plus a3 times squiggly to the third plus a5 times squiggly to the fifth plus dot 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 all the terms. So now at very large j, so at very large j, equation number 4 become very simple. It will become a sub j plus 2 approximately equal to 2 divided by j times a sub j, right? Which is the same as no, my bad. And a sub j become approximately equal some constant, let's call it c, divided by j divided by 2 factorial. Alright, so now with this approximation we can get h of squiggly to be equal to some constant c times a power series of 1 divided by j over 2 factorial times squiggly to the j, which is equal to c times the sum of 1 divided by j factorial times squiggly to the 2j, which is equal to c times e to the squiggly square. So if h goes like exponential square, exponential to the squiggly square, then psi is the thing we're trying to calculate, remember, goes like exponential to squiggly square over 2, which is exactly the behavior we didn't want. There's one way to get out of this problem, okay? Which is that equation number 4 requires some highest value of j, let's call it n, which give us that k equals to 2n plus 1. This give us expectable solution, physical solution for equation number 4. Without k being equal to 2n plus 1, where n is highest j, so this is highest j. Without this, the solution gonna blow up in our face. So what this leaves us with? This leaves us with the energy values that we want, which means E sub n equals n plus 1 half times h bar omega for n equals to 0, 1, 2, 3, dot dot dot. And now for allowed values of k, the recurrence formula number 4, equation number 4 reads a sub j plus 2 equals minus 2 times n minus j divided by j plus 1 times j plus 2 times a sub j. And this follows that h naught of squiggly, we're gonna look at the first solution here, is equal to a naught, and psi naught of squiggly is equal to a naught times e to the minus squiggly square over 2, right? And then h1 of squiggly is equal to a1 times squiggly, which give us psi 1 of squiggly time equals h1, which is a1 times squiggly times e to the minus squiggly square over 2. And let's take another one. Let's take a look at h2 of squiggly equals, remember it's gonna be in terms of a naught times 1 minus 2 times squiggly square, which give us psi 2, the second quantum state. Psi sub 2 equals to a naught times 1 minus 2 times squiggly square times e to the minus squiggly square over 2, and so forth. So all the odd numbers, all the odd psi is going to be in terms of a1, all the even psi's will be in terms of a naught. I shall not do the normalization here to show you what are a naught and a1, but maybe in the future videos if we're gonna go through it, or you can try to do it by yourself. Just integrate and try to normalize the solution to find these values. So now we are interested in the solution psi sub n. This is the solution for the Schrödinger equation for the harmonic oscillator. We're gonna put it in terms of x. Earlier we put it in terms of squiggly, but we defined squiggly in terms of x, so we're just gonna put it back. Is equal to some normalization constant m times omega divided by pi. See, this pi comes from the integration, times h bar to the 1/4 power times 1 divided by the square root of 2 to the n times n factorial, okay, times some functions, we call them Hermite polynomials, h sub n of squiggly e to the minus squiggly square over 2. So now we're gonna, let's review what are these polynomials. So we have h naught, the first polynomial is just 1, h1 is equal to 2 times squiggly, h2 is equal to 4 squiggly square minus 2, h3 is equal to 8 squiggly to the third minus 12 times squiggly a sub 4. You can look them up, but I'm just gonna list the first 4. A sub 4 equal to 16 times squiggly to the fourth minus 48 squiggly square plus 12. These guys are called the Hermite polynomials. There you have it. So this is the wave function that gives a solution for the Schrödinger equation for the harmonic oscillator. It's the same from video number 13. The only different, video number 13 we use a different method. I personally like video number 13, the algebraic method. It's more fun, it's better to work with, and I feel it gives more physical intuition than this analytical method.